Let's start. My name is Jan. I'm a bug bounty hunter, or was, and now I'm a applied cryptography researcher. I'm studying a PhD at Crocs at the Masaryk University in Brno. I would like to talk about Threshold Crypto and present you MiSign platform in the end. But first, let's start with a little motivating example. And I'm not coming from a mobile security, so you will likely know much more about that part than me, but I'm the cryptography hopefully in the room, and we'll try to oversimplify to give you the point I'm here to deliver. So let's imagine that we have some kind of bank application. We've actually seen one on the previous slide, so you can imagine that one. And there's some kind of transaction verification happening on the backend side. And of course, we have the front-end side, which can be like your standard mobile application with all the RASP and all the protection that you can imagine. And this part is doing the transaction authentication. What does it mean? And this is my sort of cryptographic assumption. It means that there is some kind of private key. There is something that resembles the user's digital identity. And so this is sort of the assumption, and I know I'm oversimplifying, but let's roll with that. So when the user wants to issue a sort of transaction, send money to someone else, they create some kind of data structure going to and from, and they need to sign this, send this transaction, send it to the bank, and now the bank does the verification of the transaction and the signature. The bank might decline this transaction because whatever the amounts don't match or something like that, or the digital signature itself maybe is not valid, but more likely everything will check out, the transaction goes through, and the respective amounts on the accounts are updated. Now, what happens if there's a adversary in the picture and it compromises the device? And now I'm giving the adversary actually quite a lot of capability, because they basically own the phone. So you can imagine maybe even the phone is stolen, or there's really serious malware. There's some 0 days, all the RASP checks, nothing works out. Hardware-backed private keys don't work out. Basically, the attacker is in. Well, now it can do basically everything as the user could previously. So it can issue some kind of transaction. Maybe for whatever reason, the attacker has screwed up, and now the backend is able to distinguish this transaction as invalid. But it's a smart attacker, and so likely everything goes through, and it has access to the private key, and so it's able to issue the digital signature as the regular user would be. And so it can actually get even worse, where maybe the adversary is quite crafty and he would exfiltrate the private key. And so maybe your anti-malware or antivirus or whatever protection is reporting that everything is fine, we've recovered, it's okay, but maybe the attacker already has the key stored somewhere else, and it can still issue the transactions and sign them digitally on behalf of the user and still continue its attack. So the question is, can we defend against this device compromise? And well, the answer is sort of, I will try to show you how you would do this with Threshold Cryptography. It's not cheap or simple. I will need to introduce one more player. In particular, let's assume that we have multiple devices. If this seems unreasonable, let's imagine that you are having some kind of asset that you want to protect with maybe your wife or your husband or your close ones, your partner, your parent, or maybe you are board in a company and you are actually responsible for some kind of digital assets, let's say. And so I would say it's not unreasonable that there is more people in the picture. If you still don't believe me, well, let's just imagine that you have a phone and a laptop and it's all yours, and you are using these ones. But it's a mobile conference, so let's take it 2 mobiles. Previously, the private key was only within that one device. However, what we can do with Threshold Crypto is sort of split the key. And I wrote share. It's not really sharing. You are not sharing the full key. You are making some kind of cryptographic magic, and you are splitting the key in such a way that the full key does not exist in a single location. When you now want to sign the transactions, you do some kind of peer-to-peer magic cryptographic dance, and at the end you end up with the same looking transaction with digital signature as previously. Okay, so this part is sort of the nuance difference compared to the previous example. And it's taking advantages of multiple devices. The very nice part is that these protocols are developed in such a way that the verification now on the backend is exactly the same. Again, maybe the bank is having some second thoughts on the actual transaction, but if it's going to verify the digital signature will check out, because the way the cryptography works, it's backwards compatible from the perspective of the verifier of the digital signature, so from the backend. How does it protect against single device compromise now? Well, let's give the adversary the same powers as previously, so it has access to the device, and now it can try to do its magic. However, even if it sort of forms some kind of documents, uses the private key share in some kind of way and sends it to the bank will always reject as long as the digital signature verification on the bank side is implemented correctly. Because the adversary doesn't have the full information to actually form or forge the signature. Maybe the adversary is feeling crafty and would actually try to do the peer-to-peer dance with the other device. However, this is where the multi-party sort of comes into play, where the other device can just stop this. And again, this is like bridging from the digital side to the real side. Like, I'm imagining that the user is knowledgeable enough in this case. I mean, it's they have the capability to stop the attack, and now it's a question like, does the user actually realize, okay, I don't want to offshore my husband's money to some kind of, sorry, I don't want to send all the money to some kind of offshore account. It's suspicious transactions, and maybe all of the other measures that we've been describing or discussing through the conference can still be applied, because I'm describing something orthogonal to all of these protections. The adversary can try to also exfiltrate the part of the key, but it did not help him previously. It does not help him even with it being exfiltrated. Of course, there's no like a silver bullet solution. If the adversary pawns both of your devices, then you are doomed in the same way as in the previous case. So the sort of protection comes from the fact that these two devices can be completely different architecture, completely different hardware stack, software stack, whatever you can imagine. And I would sort of say, well, there's also one more step. Well, let's add one more device, and now we've pushed the problem one step further. If this seems unreasonable, maybe the last device would not actually be like a user's phone, but some kind of backend service residing with the bank or with some Talsec middleman that we've seen in the previous talks. And this device on its own would not be, again, able to forge these signatures, but would be able to stop the possible attack of the adversary that has sort of attacked both users' devices. So with that, this is the motivating example done. If you've got it, you got basically everything. Now I will just go into a little bit more details and try to give you a bit more about threshold cryptography. So it's not necessarily a new thing. It's been developed already in the 80s and the 90s. The whole idea of threshold cryptography is even older in the real world. I suppose you know how like the crown jewels are stored in such a way that you need maybe 5 or 7 people to actually come with their own specific key at the same time, at the same location, and use the key. To be honest, I don't know how it actually looks in the real life, but I'm imagining some kind of threshold or multi-party cryptography in the real world. However, now we can also do this in the digital world. The popularity of the research itself and the usage of threshold cryptography is actually quite on the rise. In particular, if you know what cryptocurrencies are in this space, if the private key is lost, in many cases it means complete loss of funds forever. There's no coming with your ID to the cryptocurrency bank and asking like, oh, can you actually like revert this stolen private keys? No, like it's gone. You're done. And this is where the threshold crypto comes as nice backup feature as well. The user authentication, I mean, this is not just cryptocurrencies. So user authentication in Estonia is done in such a way that you have RSA key that's split into, I think, some kind of national agency and the user, and there's like 2 out of 2 RSA signature behind the scenes. And so it's already being deployed on a national level. If you don't know what post-quantum cryptography is and all the sort of hype, positive, negative about it, some of it comes from NIST, National Institute for Standardization of the cryptographic primitives, among other things. And similarly to how they have the call for post-quantum cryptographic primitives, they also have a call for multi-party threshold cryptography. What does this mean is that we will likely get more solutions, more interoperability, more research, more eyes looking into this problem, coming with better solutions, hopefully. One particular protocol for the threshold cryptography signatures, Frost, is already being, or already has its on RFC. It's just informational, so not the best kind of RFC you can imagine, but definitely this will help with the interoperability. Just to drive the point home, what's the point of threshold crypto is to protect the private key operations. Okay, so we want to mitigate this single point of failure where, if you recall the previous presentation, the single key of the bank, the single key of the of some kind of device or of some kind of other backend. This is still the place where we can implement threshold crypto and provide better security for this private key. You can also see this as like a decentralized storage of the private key. The private key does not exist in a single location, so it's much harder to actually steal it. Nicely enough, and we were discussing this back when we had the demo in the chapel. It's not just that the sort of creation of the signature that I was hinting at with the example is created in a distributed fashion, but it's also the creation of the key itself. And so sort of traditionally, you have your private key stored on your laptop, maybe when you are doing SSH, and it's literally like you can get the or see the private key bytes, and like this is the private key. With threshold crypto, you can have distributed protocol, which makes it so that each party ends up with some kind of share of the key, but the key itself does not ever exist in a single location. It's sort of this abstract value that if everyone uses their share appropriately, or there's enough parties that behave honestly, you end up with a valid signature later on. So this is sort of the magical part of this. What you also have, and we had sort of similar thoughts on this in the previous talks, or now can imagine, it's like different conditions under which you use your share. So if you imagine that you have a 2 out of 2 setup with your wife or husband, I think it's not that unreasonable to see that each of them have different rules to sort of see what's a valid transaction, right? Maybe weekend golf course is not a valid thing to spend your money on, but buying whatever shoes is, to make some kind of stereotypical jokes, and sorry about that. But I think you can imagine that like the conditions under which you deem something to be valid are different for different people, and you can sort of stake these against each other. You can also automate these signers with some kind of backend service and etc. To give you a little bit more sort of technical insight into how is this actually possible, I would like to present briefly Shamir secret sharing. This is not the example of distributed key generation. This is more like you have already a private value, like imagine whatever, some bytes, and you want to secret share them so they aren't stored in a single location, such that if at least threshold T of the collaborating participants come together, they are able to recreate the share. However, if you have less than T, less than the threshold, you are no wiser. There's no way how to recreate the share. In cryptography, we would call these T out of N setups, because the threshold T is needed to reach the secret value out of the N existing shares. So, basic high school geometry. Let's imagine a plane with 2 axes. Let's plot our secret value. So maybe the value is 3. So now it's not secret anymore, but let's imagine that we have some kind of value and it's plotted on the y-axis, on the vertical axis. So what we can do is come up with 2 random points, and these 2 random points have a special property that if you draw a line through these points, you actually hit the secret value on the y-axis. Okay, so I mean this is just a line in a plane, and 3 special points. One of them is the secret point, and the other 2 points are actually our secret shares. And we've created 2 out of 2, because now if the owners of these 2 points, the gray points, come together, they just plot them in a plane, they draw a line, they find the intersection with the vertical axis, and they get a value. But if you only have one of these points, one of the gray points, I mean, what kind of line are you going to draw? You can draw infinitely many lines through the plane, you can intersect the vertical axis in infinitely many points, and just like, well, go figure. And if the values are big enough, it's basically unfeasible that you will hit the point. To make this threshold, you can imagine that you will actually create more points on the same line. So maybe you add one more point, and still you need only 2 points to form the line and find the secret, and so you would get like 2 out of 3, for example. In the actual threshold protocols, and these are now protocols, it's not just a simple single signature on your laptop, you need to interact with the other parties. Tricks like these are being used, and more of these tricks to implement the distributed key generation to end up in a state where each of the participants has something like a share of the private value that they only need to interact with for later. So if later on you are forming the digital signature, you only use your share, you don't need to reconstruct the private key and have it in like one location where it can be easier to steal. Importantly, the output is indistinguishable from the like the single party case. And one of the nice feature of this is that you cannot censor the usage of Threshold crypto, right? So this means that if I were to give you one signature that I've created as a single party, another signature that I've created as a multi-party, you can be like, maybe like this looks suspicious, so maybe it's this one. But you would be guessing. There's no way for you to find this out just from these outputs. Of course, if you like have full view in all of the messages, you would see that there is some kind of interaction happening, and so maybe this would give you some kind of interaction information. But the point is that this brings it back to the backwards compatibility. Like you cannot distinguish, it looks the same, you can verify it the same. If some of the abbreviations like RSA, CDSA, EDDSA, LGML ring a bell, these are cryptographic primitives that exist in the single party case. So all of us are using these with every TLS request, etc. And now we have special protocols that implement these to make them threshold, to make them the threshold protocols that I've been describing. I'm not going through all of these like ups and downs of Threshold crypto. I've mentioned some of them, like you have the distributed key generation, but you can also deploy these with trusted dealer, and so the dealer is creating the shares, and so maybe that's a single point of failure. So there are some considerations you need to keep in mind. The backwards compatibility is quite important because you are only changing the logic on the client, not on the backend. But unfortunately, now we are juggling both the cryptography and the distributed nature of the systems. And so like all the problems, like now we have communication between the parties, we have maybe higher payload sizes. The computation itself on the clients is a bit more complex than just doing single party. When you are actually doing this, the multi-party signature, you need to discover the peers. Maybe some of the connections are dropped, like all of the problems of distributed protocols. And so it's not so easy to maybe even have a look and hands-on with these. And if you still would like to actually have a hands-on, this is where the MiSign platform comes in. So if you would like to try this and have a look, we have something for you to play with. It's called MiSign platform. And this platform is a fully open source threshold cryptography demonstrator. So I'm explicitly making this disclaimer. The point is not to give you like a production ready software that you can now go and use, but to make it easier for your developers, for your security officers who would like to see what's the newest cryptography jazz that you can use in your applications. You can go and have a play with our platform. It's multi platform for the different like Android, Windows, macOS, Linux. It's a Flutter application. I have to be honest, we are likely not using Rasp because this is just like a proof of concept application. So definitely if you open the source code, you will see places where we could improve. And we would be very happy for you to give us some collaborations or even just raise issues because everything is open source. It's on GitHub. You can just go have a look. For the simplicity of the setup, we also have a semi-trusted server who does the message relay and the peer discovery. Again, in the production version, you would likely have a bit better setup. There's a like trust on first use for the client registration, and then later on there's a mutual TLS. It has been developed by several people across several years, in particular by Anthony Duvka, who's actually in the audience, so that's very nice. I didn't know that you will be here, so nice to see you. I think you can also recognize some of the slides, so give you full credit for lots of this work, and it's been a major part of Tonda's PhD, who he successfully defended, and also Peter Schwenda, our supervisor, who has led the project for several years. this development is also because it's coming from the university, right? So there are projects behind it. One is from the Ministry of the Interior of Czech Republic, and another is from European Union. So we are quite grateful for the support here as well. Now, if you would like to use MiSign not just as the standalone application that I've been showing you in the chapel, there are also possible integrations into existing applications. So if some of these words ring a bell, or some of these standardized interfaces like PKCS11, so if your application supports the cryptographic middle layer through PKCS11 to like some kind of cryptography library or maybe hardware token, it's likely that you could already use MiSign, again, rather for demonstration than production ready. This would be not advised at this point. What does it mean? And I've also shown this in the chapel. You have SSH, and you can tell SSH, go use MiSign for the signatures. And so you register your public key coming from the threshold group to the server, and whenever the server challenges the user to log in, you actually can just tap on like your phone, your desktop, and maybe the backend service will sign automatically as well, and you get like 3 out of 3 setup, and you are logged in into your server. We've successfully done the PKCS integration also with X-Road, which is national level data exchange agents system in Estonia. It worked without any changes to the backend, except like configuration of the actual PKCS11 shared library. OpenSSL since 3.0 has providers. One of these providers is PKCS11 provider. And so while we are in the process of testing this, it should be possible to have your application, call the provider, call the OpenSSL that goes through the PKCS11 provider, that goes to MiSign, that initiates the communication among the group, and the cryptography happens in this way. And so you don't have to change your application. Maybe you just need to start it up and configure it a little bit differently. The features of MiSign, first you sort of have to create a group, so you give it the name, find the participants, you set the threshold, is it 2 out of 3, is it 3 out of 5, 7 out of 11, or is it full group, so n out of n. What's the purpose? So for demonstration, like do I just sign PDFs, do I sign random challenges? You can also do threshold decryption, so someone encrypts, but only after the quorum of the decryptors comes together, you are able to decrypt the payload. You can also pick the underlying protocol, because now there are many more protocols than just the single party in the single party case. And the users can then approve, decline. This is where the multi-party nature comes into play. There are several supported protocols, and there are some advanced features like share weighing. So let's imagine that you have some kind of setup where someone has higher rights, higher responsibility, and so you can give them like bigger shares or bigger number of shares. And so when you need to reach the threshold, it's easier to reach it with this participant, because instead of 1 share, they have like 2 or 3. And so this then affects the resulting signature. To see it in action, and I will just click through this because likely you won't be able to read anything, but it's a Flutter application, and it has sort of the whole walkthrough, like creating a group and enrolling, not enrolling, and then going through the actual signature. So we have like a first screen, there's no groups. We want to create a group, so we give it a name, find the participants, give them the number of shares, and pick the protocol, the purpose. Then this is the multi-party. We wait for the participants. Do they join? Do they not join? Right? This depends on the out-of-band discussion. What's the board maybe, or the wife and the husband, how are they going to decide? And then you end up with the group. You can check the metadata. And that's it. And when you are actually signing, let's say you are signing PDF, so you first pick the file, you pick whatever group. So now this is not the single party case. So you need to discuss like, okay, with what kind of key I'm going to, what kind of like group that represents the key I'm going to sign this. And this is the crucial part where the participants of the group can decide, do I join, do I not join? They will review the action, review the transaction, the PDF, whatever. If they like it, they can join and sign. And then you have the PDF signed, and that's basically it. So to conclude, because I'm over time, sorry for that, threshold cryptography is practical. Hopefully I've persuaded you. There are ways how to try it, for example, with MiSign. Though for real production, you would likely get more targeted solution and not use this full platform. The whole point is to defend against single key compromise. So whenever during this conference you heard the word key, private key, this is where Treasury Crypto can step in and improve the situation, because now you are staking not just single device, not just single hardware backed device, but you have multiple devices. And maybe there's some backend service included as well in the decisions. So it's a private key protection. And we have a MeSign platform, fully open source, available on GitHub. It's comprised of various repositories. This is not just like a single repo, but feel free to come to there, check it, try to download it, run it in the Docker, report any kind of issues you find. And with that, these are just a couple of references, resources that you can check later on. And thank you a lot for your attention for the last talk. And this is it. I'm happy to take any questions. I don't want to take any longer from the network session, but go for it. Yes.
Can we get like one mic for him, and I'll take this one. Thanks. There we go.
Yes, thank you very much. This is very nice. I like it. I'm just wondering whether this work continues with post-quantum cryptographic algorithms. What is the state for this?
Yes, it does. I'm not necessarily the right person to comment on what's the current state, but I know that Tonda actually has a recent paper on MLDLS setup, which is a post-quantum signature scheme. And sorry, I don't know the details. I don't want to butcher it online. But if you would speak to Tonda, he could, I guess, tell you a little bit more details. But definitely, sort of to understand this, no matter whether you have classic crypto or post-quantum crypto, there is still some kind of private key residing somewhere. And so this is like one direction, whether it's classic or post-quantum, and then there is like orthogonal dimension, what's the protection of the actual key. And so yes, sort of the problem of private key protection stays with the post-quantum, and yes, there is a research trying to get there, and yes, there are already publications that are like having, okay, we can do MLDLS in roughly this kind of threshold setup, with the asterisk that now it's the protocol. So there is some assumptions on the protocol, on the already interacting parties. And so, I mean, I'm hiding a little bit behind this, but the complexity is increased. And so, yeah, there are protocols, but it depends what the current assumptions are on these protocols.
Yeah, so thanks. It looks really interesting. So if I have some, let's say, hardware capability, which by triggering it as is like a nuclear option, so like this what you have shown seems like interesting way how to have multiple people making the nuclear option decision.
Yes, I would say so. This might be the stereotypical example. Like if it could go really wrong if one person screws up. On the other hand, now it's possible to just use it like with any application. There's like it's openly published. The protocols are available. There are open source implementation. Our platform is just like putting the existing implementation together into one interface where you can play with that, but there are existing Rust, Python, whatever implementations that you can just grab and use in your application. Of course, check all the security assumptions to see that that you pass them and that the deployment would be secure. But sort of the point is, this is not just for the nuclear cases. This is already for like the backend key for the bank. Like, how do you feel about the fact that there is some kind of 32 bytes residing somewhere in some kind of like hardware device that's by a single vendor, and like all our stakes in the bank are on this 32 bytes? I'm not like saying that this is not secure, but this is sort of the best we got so far, and so the Treasury Crypto maybe could improve the situation.
Yeah, just to your rhetoric questions, I feel bad about these 32 bytes.
Okay, sorry. Hopefully you will get some sleep after the networking session. But maybe one thing that I realized while talking about this, we've heard like trustless, zero trust, and just like some of the buzzwords. I understand the sentiment, but please keep in mind that if you split the key in this way into 10 out of 10, 1,000 out of 1,000, and you don't care about the devices individual security. Well, then the attacker would just easily pawn all of these devices and there would be no security, right? So the point is you can do this, you can split the key, but you still need to protect these devices as much as you can, because if you don't update your phone because you are using threshold crypto, well, then attacking your phone is very easy, and then it's again sort of single parties only attack on the laptop, right? So this is, I would say intentionally, this is not sort of like trustless, zero trust. Like there's no silver solution for everything. This is just making it again one more step harder for the attacker. Yes, there's two more actually. Okay.
Okay, this will be last two more.
I was wondering whether the protocol allows for membership changes. For example, somebody else gets added to the group. Does this account for that?
So I don't know all the dealers with this, but what you can do is sort of key rotation. So you have the secret value. Maybe you are not trusting that laptop anymore, and you want to rotate the keys. There is one sort of in essence, it's possible you can like reshare the keys. Let's say it was 3 out of 3, and you fully remove your share. So now actually there's no possibility to recover that share, and so the previous group is stopped, which is very nice, like mechanism. You don't have to like issue don't use this key anymore, don't verify against this key, you just stop signing with your key and no more signatures can be created. But then the question is like, you can reshare into the group again, but I would say this, I mean, technically it's possible, but depending on maybe the protocol or the actual underlying signature. But the question now comes, what are the operations of this? Like, how do you, right? Like, you want to create a new group, or like technically you can just reshare the existing private key. But I think the devil is hidden sort of in how would you do this with the new key, with the new participant, so that it's secure. So we are actually quite looking into or researching, like now it's not just your key on your laptop, but there's this whole sort of operational problems with this. That's I mean, good question. That's I would say depends on the setup now.
Okay, thank you. I think I had also the same question as the previous one.
Okay, so maybe like when you saw the secret sharing, if the shimmer secret sharing, if the secret value stays the same, you can just pick a different line, right? Or you can actually pick higher order polynomials. So you can change this while preserving the private key, the private value, while preserving the public key, because the private public key relationship stays the same, and you can throw away your shares. So that the previous group cannot sign and you have a new group. So like in this essence, it's possible, but the question is how actually you would do it in practice, in like your app.
Right, Jan, thank you so much. And I think you managed the task of a lost keynote best as possible. I mean, I feel like conversation could have went on for 10 more minutes.
Oh,
so you gotta take it to the networking area. Thank you for being with us on stage, and
thanks.